The first presentation will be held by Professor Snežana Marinković. She is a full professor at the University of Belgrade, Faculty of Civil Engineering. She is a leader and founder of the concrete structures research team. She works in the field of analysis and design of concrete structures, but especially in the field of application of green concrete types and life cycle assessment. In presentations named Concrete Structures in 21st Century and Further, Professor Marinković will guide us through the history of concrete design and construction of concrete structures, as well as future perspectives. Professor Marinković, the floor is yours.
Thank you. Dear colleagues, dear friends, dear guests, it is of course my pleasure, honor, and privilege to start this conference, which is devoted to the 175th anniversary of our Faculty of Civil Engineering in Belgrade. I will start with the quote from Plutarch on listening essays that says, "The mind is not a vessel to be filled, but a fire to be kindled. Then it motivates one towards originality and instills the desire for truth." I strongly believe that this was a guiding principle in the higher education from Plato's Academy to the modern days universities, and I like to believe that it was also a guiding idea and in the tradition of our faculty, and hope that this idea will survive in the future also. Let us start with some facts, but before, the outline of this presentation will be, as Ivan said, the presentation of the development of concrete structures through history, from the beginnings through the golden age of reinforced concrete up to the current state and future perspectives. Now we should talk something about the facts. You probably know that concrete is the most widely used construction material today, globally. Its production is about 33 billion tons per year, or 4.7 tons per person per year. This practically means that men today use only water more than concrete. On this figure here, you can see the growth rate of population, cement and crude steel production over the last 70 years. And you can see gray line is population, blue line is cement, and orange line is crude steel. You can see that the growth rate of cement production is by far the highest. Also, it is expected that the demand for concrete is going to increase by 20% by 2050. But as we shall see at the end of this presentation, this forecast may be even modest. Just to get an impression of the scale of this business, I will compare two concrete dams, famous both of them. One is Hoover Dam, which is built in 1930s in USA on Colorado River, and which required 2.5 million cubic meters of concrete. This was a world record then, and construction companies were so proud and confident of their work that they claimed that this structure will outlast human civilization. 70 years after, another dam was built in China on Yangtze River, the Three Gorges Dam, and more than 10 times concrete were poured in this dam. It is about 27 million cubic meters of concrete. China is a concrete superpower. It produces almost half of the global concrete today, and there is an astonishing statistics about this production. Since 2003, China produces every 3 years more concrete than USA managed to produce in the whole 20th century. So this is really an enormous, these are really an enormous figures. All this started about 2,000 years ago in the Roman Empire. We know now that in ancient times, let's say 3,000 years BC, in Egypt, in Greece, in Babylon, in China, various types of mortars were used as binders in their stone and brick masonry works. But mostly these mortars were lime mortars. Truly, cementitious binding agent was in fact found and invented around the 2nd century BC in the southern Italy, in the Bay of Naples, where a special type of volcanic sand called pozzolana was mixed with lime and water, and in that way the cement was produced, which Romans used in all their concretes. This cement was called pozzolana cement, and it enabled the first Roman concrete. This is because this type of volcanic sand chemically reacts with lime and water to solidify into rock-like mass. Roman concrete differed largely from nowadays concrete because it was not poured, it was not constructed in the with fluid consistency. It was in fact constructed in layers by packing mortar by hand in and around stones of various sizes. And with such type of concrete, Romans built all their structures. Within them, the most famous are the Pantheon Temple and Colosseum in Rome. You can see the structure of the Pantheon. Its clear span, the clear span of the dome is about 44 meters, and it is in fact the largest unreinforced concrete dome ever built, and it is still standing. In the Middle Ages, this concrete making still was lost, probably due to the lack of availability of similar pozzolana materials all around the world. And stone and stone and brick masonry remained dominant construction material until the beginning of 19th century, when one English mason, Joseph Aspin, invented so-called improved cement, which he named Portland cement, after the famously strong building stone quarried at Portland in the UK. And he was in fact the first to use high temperature to heat finely grinded lime and clay until the mixture is calcined, and that's how the first Portland cement was invented. Until the 1860s, chemistry was understood totally, technology improved, and the era of modern Portland cement began. This cement, in fact, enabled concrete technology and properties as we know them today. The first reinforced concrete was introduced by two Frenchmen in 1848 and 1849, and this was Jean-Louis Lambeau and Joseph Monnier, although neither of their inventions was in fact structure. Lambeau made a boat made of cement mortar and reinforced with wire mesh, while Monnier made a flower pot, a concrete tub for flowers, for trees. And he was in fact, he deserves the credit of the practical use, of the first practical use of reinforced concrete in the structures. He was a clever man. He understood that this material, this new material, can have a great potential also in structures. And very fast, reinforced concrete developed both on the material level, construction level, design theory levels. And by the end of 19th century, beginning of the 20th, we already have all types of structures made with reinforced concrete. And here I chose to show you this Ingalls building in Ohio, Cincinnati, which was built in 1904, and which was in fact the first concrete, reinforced concrete skyscraper. It has 16 stories and 63 meters high. Somewhere around 1930s, the first ideas of and about pre-stressing of reinforced concrete structures arose. Again, there was one Frenchman and one German, Eugène Freycinet and Franz Tischinger, who invented the technology of pre-stressing, or the new type of concrete, which we today call pre-stressed concrete, mainly in bridge construction and design. And this new technology opened up new possibilities for spans, forms, aesthetics of reinforced concrete structures. And you can see here the first pre-stressed concrete bridge built in France in 1946. It was designed by Freycinet, and it is still in use. Okay, I have to drink a little bit water, I'm sorry. Since then, reinforced concrete experienced an outstanding development on the material level, on the construction technology levels, on design level, and today reinforced and pre-stressed concrete are successfully applied in all types of structures, so in infrastructure, building, industrial construction. And we can say that twice as much concrete is used in construction around the world than the total of all other construction materials. Now the question is why the concrete is so popular. There are several reasons, and you can see them here. So easily available and low-cost components, meaning concrete is cheap. Any structural shape can be obtained, good mechanical and durability-related properties, fire resistance also good, and low maintenance cost. In a word, best ratio between quality and cost. Now we came to 21st century, and we all know that modern age requires, no matter which construction material we are talking about, fast, quality and cost-effective construction, as well as functional, robust, durable and sustainable structures. In the last 40 years, the composition of concrete was significantly improved, and we have now many new types of concretes. It also developed to modern cement composites with very high mechanical and durability performance and improved cracking and fracture behavior. At the same time, this happened mostly owing to the invention of chemical admixtures like plasticizers and superplasticizers, due to adding different mineral additions, inventions of fibers, and so on. At the same time, mixing and casting methods were also improved, and the new construction technologies, innovative construction technologies were introduced. Design theories grew from intuitive through working set method to the performance-based design, which we today use for design of concrete structures. We also should say that, and we all know that, of course, that the 21st century imposed the sustainability imperative upon all human activities, and the construction technology, of course, is no exception to this rule. And that is why we need our traditional technologies, methods, and practices to adapt to fulfill the new requirements, and this led to a special type of concretes, which we call today then green concretes or green concrete solutions. Now I will say just a few words about all of these new concrete types, which are mostly developed in the 21st century. First one is so-called fiber-reinforced concrete, which is a type of concrete where fibers are added to improve concrete's cracking and fracture behavior. And if you put short fibers in concrete mix while mixing it, it will be randomly distributed and embedded in the cement matrix, so it will somehow, as you can see on this figure, bridge the cracks. So fibers enable reduced cracking, generate post-cracking residual tensile strength with relatively large tensile strain, and in that way turn the brittle behavior of concrete into, let's say, strain hardening or strain softening type. We use usually steel, carbon, glass, plastic fibers for fiber-reinforced concrete. Natural organic fibers are also used, but they have an aging problem, and care should be taken when they are used for structural concrete. Some properties that are improved with this type of concrete you can see here. So several times higher fracture energy, higher resistance to impact stresses, shrinkage cracking minimized, better resistance to corrosion and abrasion, and high resistance to elevated temperature if plastic fibers are used. Due to that, this type of concrete is usually applied in industrial floors, precast lining tunnels, as you can see here, pipelines, in repair works, in shotcrete, and now there is an ongoing research related to the application of this concrete in structures, but without any conventional steel reinforcement. If you use long fibers instead of short and put them in the direction where you anticipate the tensile stresses and strains, you will get the so-called textile reinforced concrete, which is generally concrete reinforced with non-metallic reinforcement, whether in the form of bars, 2D or 3D meshes, and usually carbon, glass, and basalt fibers are used. You can see this textile or 2 or 3D meshes, which are made of carbon, glass, or basalt fibers. And since it looks like a textile, this type of concrete got that name, textile, and not only looks like, but these meshes are produced in the similar way as textile fabric. At this moment, this type of concrete is used only for strengthening of reinforced concrete structures, while application in new structures is still limited to the initiatives mostly in Germany. And you can see here 2 examples. One is a footbridge built in Germany in 2004. Instead of steel reinforcement, it has glass bars, and the span is 8.6 meters. And on the other figure, you can see, as they call it, the first building made of carbon concrete. It is called the Cube, and it is at the moment under construction at Technical University of Dresden and their campus. It is in fact the structure which is reinforced with carbon meshes, so it is a textile reinforced concrete. All the Germans like to call them carbon concrete. Another new type of concrete which was developed in the 21st century is so-called ultra-high performance concrete. Invention of plasticizers and super plasticizers enabled us to produce concrete with the compressive strength which is higher than 50 to 60 megapascals, which was in fact the upper limit for, let's say, ordinary normal strength concrete. Since 1980s, first high strength concrete was developed with the strengths up to 100, 120 megapascals. And since 2000, we now have developed concretes with very high strength, which is up, as you will see, it can be up to 800 megapascals. This type of concrete is in fact a cement composite, which contains a large amount of ordinary Portland cement. It must have low water to binder ratio. It must have highly reactive additions such as silica fume. It has only 5 aggregates, sand, with quartz powder, and of course it must have high performance plasticizers. Depending on the temperature of curing, it can reach 200, 400, 800 megapascals if you apply pressure also. Tensile strength and modulus of elasticity are also much higher than for conventional concrete. It has excellent durability, but it is a brittle material, so to compensate for brittle behavior, usually fibers are added, and that's how we get ultra-high performance fiber-reinforced concrete. Here I'm showing you a few examples of the application of this type of concrete. First one I chosen because it was the thinnest concrete shelf ever built. This is a Shonnes railway station in Canada from 2004, and in fact ultra-high performance fiber reinforced concrete was used for these precast canopies, and the thickness of this shell was only 18 millimeters, so as we are looking at steel structure. Professor Veljković, am I right? You can see also several pictures from the construction of this extraordinary structure. And the other example that I chose for you is the Museum of European and Mediterranean Civilizations built in France, in Marseille, in 2013. Ultra-high performance fiber reinforced concrete was used for facade. And you can see this is also an impressive architectural concrete, in fact. However, these outstanding properties of this type of concrete come with costly and sophisticated technology. Also, the sustainability of such type of concrete is questionable, because although you can largely reduce the volume of your structural members using this type of concrete, and you can enable prolonged service life because of its excellent durability. Still, you need to put high amounts of cement, of silica film, you need high energy consumption, and therefore the sustainability of such concretes is questionable. So far, they are used only in, let's say, extraordinary projects, mostly in bridges, and as architectural concrete, as you can see here. Self-compacting concrete is developed also in the 21st century. This is a concrete which de-aerates and floats without the application of compaction energy while staying homogeneous during the whole placing process. It means it can be casted without vibrating, and it has a larger amount of paste. Due to this fact, it can be casted in this way. The paste usually consists of cement and large amounts of fly ash or limestone powder, and of course it must have super plasticizers. Finally, green concrete. We all know that the construction industry imposes large environmental burdens, large consumption of natural resources, especially fossil fuels, large emissions of various substances that pollute the air, the soil, the water, and also large amounts of generated waste. Concrete in particular has a problem with large CO2 emissions because of the cement production, which is responsible for almost 7 to 8% of the global CO2 emissions in the world. So it is of crucial importance for us to find the ways of greening the concrete construction, concrete industry in general, and this is done mostly in these three ways that I put here. One is recycling of construction and demolition waste, the other is the replacement of cement with so-called supplementary cementitious materials, and the third is on the design level by design for longer service life and reuse. Green concretes can provide us with lower environmental impact. They can be produced with comparable mechanical properties as conventional concrete, but they usually have a lower durability, especially when we are talking about carbonation resistance. Whichever supplementary materials or filler or type of aggregate we use, our aim is always to keep the structural performance of concrete at the desired level. Up to now, an extensive research in this area was performed, and although we already have technologies and design recommendations for such type of concrete, their application and use in structural concrete is not yet standardized. And if it is allowed with strong limitations that cancel eventual benefits. What to say about the construction technologies in the 21st century? There is a saying in construction world that construction hasn't changed much since the times of pyramids. It's all about moving workers and materials. And it is true, it was true until the emergence of 3D printing technology. The highest level of industrialization and automation that we had in concrete industry was in fact precasting, prefabrication of structural members. But nevertheless, using precasting in combination with pre-stressing and advanced construction machinery that was advanced during the 21st century, we were able to build impressive structures, and I will show you some examples of them. First one that I chose is a turning torso, which was built in Sweden in 2005 with a height of 190 meters. You may maybe ask why this building was called the turning torso. You will see now. This is because Santiago Calatrava, which was the designer of this building, had such inspiration. So one man's idea, many men hard work to realize it, because it was not easy to build a structure which rotates for 90 degrees from its bottom to its top. But everything was built with conventional construction technologies. Then, of course, I have to mention the tallest building in the world, and tallest man-made structure. This is Burj Khalifa, you probably know. It was built in 2009 in Dubai. Its height is 830 meters almost. And for the construction of this building, a special concrete pump was created, which set a world record for vertical concrete pumping at 606 meters. That enabled, in fact, the construction of this building, which primary structure is in reinforced concrete, conventional. Then there is the tallest bridge in the world. It's Millau Viaduct in France, built in 2004. The highest, tallest column has a height of 343 meters. This is higher than Eiffel Tower in Paris. Again, conventional construction technologies. Since 2000, we introduced a special robotic technology, construction technology in concrete construction, which is called 3D printing. And with its introduction, radical changes in construction began that parallel the changes automation and robotics brought to the industrial complex in the 70s. This is an additive technology construction. Building is created from ground up in layer-by-layer manner using giant robotic arms. Entire buildings can be printed on site, and of course this technology allows faster construction, allows building complex designs, lowering labor costs, producing less waste, construction under harsh and dangerous conditions like in space. Of course, there are many unresolved questions, such high cost of equipment, specific skilled labor is needed. There is a question of liability if you use robots instead of humans. There is a question of adequate concrete composition, how printed structures will incorporate services and reinforcement, and so on. Due to already developed giant robotic arms, we have now outdoor printing, and we can print the whole buildings. And you can see this is this arm. You can see some examples here. And in the last decade, several let's say innovative construction projects were built with this technology. Here you can see the first office building, the first 3D printed office building in Dubai. Its construction lasted less than 17 days. Then here you can see the two-story house. This is now China, Shanghai. It was built in less than 45 days, included embedded reinforcement and services in the walls. Here you can see the largest, so far, the largest 3D printed bridge, which has a span of 26 meters. And finally, one example from Europe, first 3D printed home in Europe, in Eindhoven, in Holland, in 2021. And this is a house where people actually live. I will not talk much about design since I don't have time anymore. I will just say that design of concrete structures progress from intuitive through working stress methods to performance-based design, which is based on limit states. And I would just like to say that the model code of 2010, this is a concrete code, European concrete code, was first to introduce the performance requirements for sustainability, and they were related to impact on environment and impact on society, but this is so far as I know, the only code which introduces sustainability as a design criteria. Further development of modern cement composites, like ultra-high performance concrete, textile, fiber reinforced concrete, self-compacting concrete, but since the cost and the impact on the environment of such cement composites is much larger than in the case of conventional concrete, research is needed and efforts are needed to reduce the cost and the environmental impact of these new concrete types to enable their wider application. Then I didn't have time to speak about one special technology, which is called fast carbonation of recycled concrete aggregates, which is used for decarbonation of the concrete sector. It is a very interesting technology, and it is expected to be developed at large industrial scales very soon. Then we should incorporate all these new concretes, especially green concretes, and performance criteria for sustainability in new international codes, of course. And, of course, fast development of 3D printing technology is expected in the future. Concrete came a long way from Pantheon Temple to Burj Khalifa. In less than 200 years, it developed in a cost-effective, versatile, durable construction material with mechanical properties good enough for most of our structural purposes. But still, recently, concrete got a very negative connotation in various types of media because its impact on the environment and on mental and physical health and so on. It is true that many things on which our future health and prosperity depends is today in danger, like climate stability, like resilience and productivity of natural systems, like biodiversity, and so on. And somehow we found ourselves in the situation concrete versus nature, in which battle concrete was claimed as a main villain, which causes all our problems. But is it really true? Is it concrete's guilt, or maybe it's man doing? Look what we do to provide the roof of our heads, food and water, to protect ourselves from natural disasters. Look at these two structures, both from Japan. One is a seawall in Yamada, protection wall, and the other is water tank in Tokyo. Look how small man looks compared to these giant structures. Still, we all want to live in cities. Still, we all want to pay the lowest price for our homes. We all want to use cheap energy. And almost half of the world's population already lives in cities. This was something about somebody already was speaking. And the forecast of the United Nations Population Division, you can see on this figure. Now we are 2020s, this is here. And this is about 4 billion people living in cities at the moment. By 2050, the forecast is that 6 billion people will live in cities. Now the question is, how much concrete shall we need in the future? On the other hand, no alternative to concrete as a major global construction material currently exists that can replace concrete at sufficient scale. I don't have time to elaborate this issue, but believe me, this is a fact. So we are stuck with concrete. So we need to raise the trust in the use of green concrete solutions. On technology level, to develop more efficient and cheaper production technologies. On economy level, to implement measures, to stimulate the use, and on the society level, to transfer knowledge from science to industry, and to constantly educate about the benefits of green concrete solutions. And finally, if there will be no place on this planet for concrete, there will be on others, certainly. 3D printing is in position to be a viable solution that offers key benefits for our building's future. This robotic technology can enable us to build habitats on Mars and Luna, and in fact, we are already preparing mixed designs and compositions for concrete which can be produced on Luna and Mars. So, for concrete, we can say the world is not enough. Thank you for your attention.
Dear Professor Marinković, thank you for this inspiring presentation, this historical overview, but especially for sharing with us your vision of concrete structures. I would say that this was a journey by concrete path to the moon and back. Now I'm opening discussion. So is there any question? Professor Veljković, please.
Thank you.
So when you're talking about concrete as a main problem in construction sector, I just want to hear your comment if the cement is actually the problem, not concrete itself. And what is the development in that direction? You mentioned a couple of alternatives for cement. From the point of view of steel structures, we are very much interested to have a green concrete based on geopolymers, because we are using that for making composite decks. But it does not work sufficiently good at the moment, and I think it is important to develop such type of concrete mix based on geopolymers without cement, where you can have addition between the zinc layer that we use for profile sheeting and the concrete, because one of the most important structures for construction sector is when you mix concrete and steel, because it is the most natural to use steel in tension and concrete in compression. So there is a potential to make concrete more greener, but how is it going with that in your mind? Thank you.
This is true. Cement is most responsible for all CO2 emissions from almost all, 18 to 90% of CO2 emissions from concrete, in fact, is emissions from cement production, and half of them cannot be avoided because they are the result of a chemical process, calcination. So we can only use other types of fuels to reduce CO2 emissions, but half of the CO2 emissions we cannot avoid. So one way to make a greener concrete is to replace a part, if it is possible, the whole amount of cement with something else which has a low embodied CO2, and usually reactive wastes from other industries, like fly ash, for instance, and blast furnace slag, are used for the replacement of cement. Also, today we use limestone powder as a filler and as a replacement of cement. And these concretes are called high volume fly ash concrete, recycled aggregate concrete if you use recycled aggregates instead of natural. High filler content concretes, and so on. But if you speak about geopolymers, we tried at our faculty with such type of concrete, and we also were not successful very much. This is for the public. This is a type of concrete in which the whole cement, the whole amount of cement is replaced with, let's say, fly ash or some other type of mineral addition. But if you use fly ash, then you have to heat the concrete, and this is the reason why we thought that it is not applicable to on-site structures, only for precasting. And we also had the problems with workability of such concretes. So we managed to produce structural concrete with adequate mechanical properties. It can be done, but you need an energy to heat it, to get the adequate mechanical properties. And this is, in the end, you get a concrete which has lower CO2 emissions, it has lower GVP, but it has relatively large energy demand because you need to heat it to get the properties that you want. So, but it is of course a possibility. In Australia, they use geopolymers, I think already at large industrial scale. It is a possibility, of course. And composite structures, of course, concrete plus steel. This is also future. Okay, is it it?
Thank you. Professor Butinek.
Yeah, so thank you for the really nice presentation. So I have a question regarding the application of green concrete for carbon reinforcement or textile reinforcement. Is it possible to use the green concrete because you are substituting some of the ingredients? And as far as I know, it was always quite difficult, let's say, to ensure the bond between the cement or the concrete and the carbon or glass. And my second question is, it was also always a big problem with the corrosion of the glass reinforcements. So can this cause some problems if you change something?
First question is about using green concretes in textile reinforced concrete. We didn't try it. I'm not aware if anyone tried so far, but it is possible, of course. Only any concrete that is used in textile reinforced concrete must have a very fine granulation, so you cannot use coarse aggregates. You must use only sand and finer aggregates. So I suppose it is possible, but I'm not aware that there are research in this area. Maybe there is, but I don't know.
That's quite important, yeah. It's quite important, because otherwise that's contradictory. So then you have new innovative materials, and on the other hand, you cannot combine it with, let's say, this green concrete, which is, I think, rather important.
Well, the replacement of reinforcement, steel reinforcement, with some other materials such glass and so on, carbon or any other fibers, in fact started from the desire to eliminate corrosion and the impact of corrosion on durability, on service life of concrete structures. And if you use short fibers, this is true. So you will really have better corrosion resistance. But if you use bars or meshes, it's a problem again. It's a problem. But textile reinforced concrete is not so widely researched. I know about Germany.
I think only a few buildings were erected so far, so the applications are more related to
strengthening.
Let's say, strengthening, and probably, so there are some special elements produced that are often used. So, but it's not, let's say, that you can really apply it to the construction
to new structures.
Yeah. It's really difficult because there are a lot of problems. Okay, so I think we do not discuss it now.
Okay,
Thanks.
thank you.
Yeah, Professor Lopresti.
Davide Lopresti, University of Palermo. Thanks for your very interesting presentation.
Thank you.
I work in the field of roads on pavement, but I see a lot of similarities from what we're doing in terms of sustainability. So I had a couple of questions, very quick. Are you already considering estimating what is the durability of infrastructure components in buildings? Whenever we apply life cycle thinking, having the durability of a component is key for any calculation. So are you already working on, for instance, says this pillar is going to last 10 years, or this roof is going to last 15 years, and do we have clear number about that?
Okay.
And my second question is really your opinion on self-healing concrete, which is a technology that I didn't see mentioned, but possibly I can have your opinion. Thank you.
Thank you for your question. First one was about the durability. Now we design concrete structures taking into account the required service life. So we today know when we design a structure how long it will last, 10, 20, 50, 100 years. So this is now design criteria according to Euro codes. So we are taking it into account. The second question was about, remind me please.
Self-healing.
Self-healing concrete, yeah.
Yeah.
I don't know much about that subject. I know that there was research, maybe even you can help me with that, self-healing from Holland.
Yeah, there's a lot in that. Yeah, but it was just...
with these bacteria making calcium carbonate.
Yeah, bacteria, yeah. Milane, maybe you know more about that.
Perfect. Just going back for the durability, how do you account for that? So whenever you say a certain component will have a certain reference service life, do you have an idea how you can get that number?
When we talk about the structures which are reinforced with steel reinforcement, then we have some mechanism that we count for, let's say, steel corrosion due to carbonation or chloride ingress, and we have to calculate the concrete cover, which is a sloy of, which is a layer of concrete with which we protect our reinforcement, and we need to calculate the depth of this concrete cover to provide for certain years of service life. So if you need 50 years of service life, then you will have to put, let's say, 5 centimeters over your reinforcement, and if you need 20 years, you will put 2 centimeters of reinforcement. This is in fact not, these are methods based on experience, not so much on real chemical and physical modeling, but this is also going to enter the code, the future codes, I hope so. Okay.
Thank you.
Thank you.
Maybe I can add that now we have models for durability prediction, and we call it service life design. So it is a kind of design similar like you do it for ultimate limit states or serviceability limit states. So you can also design for durability, let's say, limit state. So we have models that in which different parameters are combined, and which we have also safety factors for different reliability index. So for different reliability, so probability is in the back of these models. So a lot of parameters, because this is physical and chemical processes which needs actually a lot of parameters. But we have models that describe, but only carbonation, as Professor Marinković said, and chloride ingress.
Yeah, but this is not in standards. This is not yet standardized. So standard practice when you design is only to choose the depth of concrete cover, nothing else. Okay.
Okay, so with this I will finish this session, this first half of the session.